Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Dan selamat pagi. Kita mulakan dengan bacaan kita Al-Fatihah. Alright, so today we will learn the next chapter. Alright, so far we have covered the first chapter, which is an introduction of astrophysics. Now we move on to the second chapter, which is related with the lights and matter. Right, and as we know that the light is very, very important in astrophysics topic, because from the light we can determine a lots of parameters. Yeah, and we also talk about the matters, because we know that the stars, yeah, the planet and so on is a part of matter. And in this case, right, there's a few topics that we need to know, okay, which is the stellar parallax, and we want to study what is the magnitude scale, yeah, which is related with the brightness, and also the color index, okay, because we know that even the star also have the colors, different colors. And then we move on to the stellar spectroscopy. All right. So as a part of introductions, we know that in the last subtopic from the first chapter, that we can determine the energy based on the electromagnetic spectrum, right? The gravitational radiation, and also based on the particles. And we understand that the light has been recognized as the electromagnetic waves that covered from the gamma rays to the radiation, to the radio region. Yeah, and most important source for the astronomy is actually the light coming from the celestial object. And this is characterized by the transverse electric and also the magnetic field. So I'm sure you learned in the second year about the magnetic fields, yeah, and this is important to you, right, to understand how does the charged particles interact with the light emitters, and the direction of the propagations being the right angles into those fields. Okay, so if we look through the parallax, we understand that it's not just in the experiment, okay, but somehow it also be used in terms of the astrophysics. And we understand that we do have the distance from the sun and also the earth is about 1.5 times 10 power of 8 kilometers. So this is equivalent with the 1 AU, or 1 astronomical units. And we want to see the other objects. So if we look through the stars, we understand that it's not just the stars is moving. Our earth, our sun also moving at the same time, and they do have the parallax, right? So we want to determine the parallax angle first before we can detect the distance. So since we can, based on the trigonometry parallax, so we can get the angle, right, of the parallax angle. So this is the distance between 1 EU, which is between the Earth and the Sun, and then we can also get the angle, right, the stars of the stars in between of the Sun, also the Earth. Okay, so we can detect from there, and this is how the starting point of measure the distance of the stars. Okay, so what is stellar parallax? This is the apparent displacement or difference of orientation of the object viewed along two different line of sight. So we can see based on the schematic diagram before, we do have the two different lines of the sight, and it's measured by the angles or semi-angle, right? So in that case, we can see the semi-angles of inclination between the two lines. So we can get the angle based on the two lines. And the diameter of the Earth orbits around the Sun is used as a basis of line, right? And this is what we call as a trigonometric parallax. So it based on the mathematical methods at the same time, and from there we can calculate or we can measure the distance of any stars. Okay, all right. But somehow, of course, it's not that easy, yeah, because we need to understand that it's moving. So we need to do the measurement few times, right? A lot of times actually, and then to confirm that that is the distance of the stars. Okay, so why the distance is very, very important, right? Since we know in SI units is also one of the main SI units before we can determine the other parameters. The distance are necessary for estimating the total energy emitting, right, by the object. So we can get the luminosity, for instance, the brightness of the stars based on the distance at the same time. So this is the main parameters that we need to really confirm, right, before we can get the other parameters, the right or the correct unit for the other parameters. From there also we can calculate the mass, right, the true motions, the physical sizes, okay, and also the other parameters. But somehow, right, to measure the distance is very hard, right? So that's why we need to understand that it takes a lot of time to measure the distance for the first part before we can get the other parameters. Okay, right. So we also understand that it's not just one star we can observe, but there also a foreground stars behind it. Okay, so the stellar parameters is the difference in direction of the celestial object as seen by observer from two widely separated points. But somehow, okay, we know that we do have the geocentric parallax, right, which is from the Earth, and also heliocentric parallax, which is from the Sun. Okay, so the position of the observers and the position of the objects formed a triangle. So this is kind of starting point, but we need to understand that we need to get a good method to calculate the distance. Yeah, and we also understand that there's a lot of billion of stars out there, so we need to calculate one by one, right? So it needs a lot of time for calculate the distance. Okay, so somehow if you look through the method of the trigonometry parallax, yeah, for instance in December, um, we know that our Earth at certain point, right? For we can see there is also another point if we are at the June. Yeah? So at the same time, we do have the foreground stars, okay, and the distant stars, which is far, far away from us. So we need to make sure that we are calculate the right stars first. That is the first one, and at the same time, we also need to make sure that where are we, right? For instance, we in at June, right, or maybe we are in December. So this is important for us to know that that is the stars that we measured. Okay, all right. So there is what we call as the stellar parallax, and this is the apparent motions, which is not a true motions, yeah, from the stars. So we can see there's a lot of factors that we need to consider before we want to calculate the distance. Okay, somehow, of course, as the distance is increases, right, the parallax will decreases. So this is based on the schematic diagram here. We can easily get simply logic formula, yeah, from here to relate the relationship between the distance and also the parallax. So in this case, we put the distance as a D unit and the parallax as P unit. So we can see that as the distance is increases, right, the parallax is decreases, right? So we can see the angle value here. For the case of the below diagram, for instance, okay, this is the angle will be very small when the distance of the stars is increases. Okay, and of course, we can calculate in arc second unit. So please um, remember what is a second, yeah, what is a minute, okay, because we calculate using the arc length, yeah, and we know due to the circular motions. And even Proxima Centauri, which is the nearest stars, yeah, still are very far away, and it is about 0.772 arc second. So this is been observed in 1837, all right, by Friedrich Bessel, and in the Sydney constellation. So we can see that even the the nearest stars is very, very far away, 0.772. So it's based on the value of 0. So just imagine the other stars, right? So it can be 0.00 value, okay, 0.005 values, for instance. So it's not easy to measure from the Earth, okay? And if we calculate using the telescope, for instance, okay, we can see that um, this is the things, okay? So we can get a lots of stars there, okay, based on the view image, based on the quite large size image. So this is also has a different size, okay, and quite faint. Okay, some of them is bright, but some of them is faint. So we need to understand that, and also know that that is star that we want to measure. And if we look through the formula here, so since we can see based on the schematic diagram, and therefore we can create that the t is actually inversely proportional with the parallax. So t equals to 1 over p. And in this case, the p is actually the parallax angle in that second, while the d is actually a distance in parsecs. Okay, all right. So you need to also understand what is parsecs. This is actually a parallax second, right? And there is a relationship between the unit of the parsecond or parsecs with the kilometer and also AU. Okay. So in this case, right, what is a one parallax, okay, or one parsec, okay? So this is equals to 206,265 AU. So just imagine one parsec is still very, very large, yeah, because we understand that one AU is actually the distance from the sun to the earth. So just imagine this is 206,265 AU, right? So this is equivalent to one parsec. And this also equivalent to 3.26 light years, which is equivalent to 3.086 times 10 power of 13 kilometers, right? So another terms, which is light years, and this is actually a distance traveled by light within 1 year. So just imagine we want to take one complete cycle within 1 year, which is 365 days. So that is actually equivalent to the 1 light years. And this 1 light years is equivalent to 0.31 parsecs, which is equivalent to 63,270 AU, right? 60,270 AU. And basically we use a unit of parsecs for the distance of the star, because this is of course a far, far away from us. Okay, and most of the science book like to use the light years because it's more popular rather than you need a parsec. Okay, right. So if you look for examples, yes, this is Alpha Centauri, which is about 0.742 a second, and when we want to calculate the distance, this is equivalent to 1.35 parsec. Okay, and another stars, okay, for instance, if we want to measure the p equals to 0.02 a second, so we can get about 50%. Okay, and we can also convert it into the astronomical unit or maybe in light years. Okay, right. Somehow, of course, the unit parsec is PC, and of course it used to measure astronomical large distance to objects outside of the solar system. And we can have the nearest star, which is a Proxima Centauri, and this is equivalent to 1.3 parsecs from the sun. Okay, most of the visible stars to the unaided eye in the nighttime are within 500 parsec of the sun. So we can see or roughly know the distance that is a bright star, or things the star that we can see at the night. So this is about 500 parsecs mostly, all right, of the sun. Okay, but somehow there's also a limitation of the parallax, because if the stars are too far away, the parallax can be too small to measure. So you just imagine, because of the angle, it's not easy to get zero angle, 0 point something something, right? So it's not easy to measure accurately. Okay, and of course it do have limitations. And first, it is good out of only 100 parsec, okay, and but somehow only 10% distance are out of the 2 parsecs, because mostly the stars is more than 100 parsecs, and only a few stars or a few hundred stars are this close. Okay, so it's not easy if we want to measure from the Earth. Okay, we need to get the data from space telescope. All right. So that is about the per second, right? So we can discuss in the next session. Okay, and now I move to the magnitude scale. Okay, if you look to the magnitude scale, this is something that related with the brightness, and it starts from the second surgery by Hipparchus, which is classified the stars. He can classify the stars according by the apparent brightness. So we call it as a kecaran ketara. It's something that we can see directly. Okay, and he managed to catalog about 1,000 stars and group it into the 6 group. Okay, so in the first group, he put as the brightest stars until the next one, right? So means that the last one will be the faintest stars. And then in 1830, the William Herschel start his experiment in the photometry by determining the first magnitude, which is 100 times brighter than the stars of the sixth magnitude. Okay, so from there, the R person. R person is the third person who constructed the quantitative scale in a precise physical basis, and he managed to catalog or define the magnitude scale by do the ratio in the first stars to the sixth magnitude, right? By 100 with the 1. Okay, so this is the ratio between first magnitude stars with the sixth magnitude of the stars. And Watson also calibrate the 0 point of the magnitude scale with the reference of the faintest detectable stars. And based on that, he put as a B1, B2, and until B6, right, respectively. So we can see here, when we put as a ratio, we can do mathematical methods, whereas B1 over B2 is equivalent to B2 over B3 until to B5 over B6. So we can put as X, right? So this is part of the ratio process. And then to get what is the power of the first and the last one of the brightness, so which is equivalent to B1 over B6. So this is X power of 5, right? Since we understand that the brightness is 100 times larger, right, compared to B1 and B6. So we can put that as 5 is equivalent with the 100. So from there, we can get that the X is equals to 2.512, right? So this is the ratio between each one, okay? And if we do have Bm, right, as a integer, any integer, and Bn, while the n is larger than Bm, so we can put that the Bm over Bn is equivalent to 2.512 power of n minus m. So it based on the ratio that we have do the construction before. Okay, so then we can get that log Bm over Bn is equals to n minus m log 2.512, and from there, since we know that log 2.512 is equivalent to 0.4, therefore we can put it as a 0.4 n minus m, right? And this is give the results that Bm over Bn is equivalent to 10 power of 0.4 times with n minus m. So it shows that the relationship between two different stars is based on this formula. Okay, so the higher magnitude of the stars means that the less brightness it is. Okay, so you need to understand that if we do have the stars about 20, for instance, that's so which is larger compared to 11. So it means that it is less brightness with the 11 one. Okay, so for instance, we do have the value of negative So it means that it's much more good compared to the positive one. And our star series, for instance, we do have 1.4. Our planet is 4.4, negative 4.4. So we know that the sun is the brightest one, and this is actually negative 26.8. So it will give the negative value to show the brightness of the objects. Okay. All right. So what is apparent magnitude? Okay, we can put it as a M, and this is actually the how bright a star looks to the observer. Something we can see, so that is what we call as apparent magnitude. So this is actually the energy flux, right? That which is also the energy that received per second per square meters at the position of the observer. And we can also, based on Hipparchus, which is a create a 6 categories, and he put that the magnitude 1 are the brightest one, right? Which is a naked eye. The magnitude 2 is the brightest naked stars, right? And then this magnitude 2 are fainter, okay, and then magnitude 3 even fainter, okay, and so on. So we can see that when the magnitude values is higher, so it will be a faint objects. Okay, right. So as a part of physics, we know that the F is equivalent to luminosity divided by the area. And in this case, we can assume it's a sphere, so we can put as a 4 pi r squared. Okay, and this is measured in watt per meter squared, and the flux is actually related with the intrinsic energy and also the area. Okay. All right. So what is luminosity? This is actually a direct measure of the total energy radiated away from the stars and expressed in joule per second or watt. Okay. So we can put as L equals to 4 pi r squared times with the flux. Okay. And for the solar luminosity, the value is about 4 times 10 power of 26 watt. And this is equivalent to 1 L dot. Right. So this is actually represented by the sun's luminosity. Okay, and we put luminosity also can call as the absolute brightness. Okay, but somehow it's actually two different way of the expressing of the measurement. Okay, right. So another examples of the past examples. Okay, we can see that each stars is also moving, and then we can get the angle based on the two main lines here. Okay, all right. So the next topic is about the colors. Okay. And we know that the stellar colors are numerically based on the UBV, and it based on the visible wavelength, right? So ultraviolet, B is equivalent to blue, and V is actually visible. Okay. And in this case, we do have, for instance, B minus V means that the B is larger than V. Okay. And since we do have UBV filters, okay, so it do have a different wavelength. Okay, so for instance, U is actually the ultraviolet magnitudes, and it's actually centered at 365 nanometer with the effective bandwidth about 65 nanometer, while the blue one is actually a blue magnitude, which is measured through a filter centered at 440 nanometer with the bandwidth of 98 nanometer. And this is difference with the ultraviolet magnitude. And the V, which is visual magnitude, is measured through 550 nanometer with the effective bandwidth about 89 nanometer. Okay, so I will explain details on this in the next lecture. Okay, and we also have the Johnson Cousin filter response, which is additional of R and I filter, and this is up to infrared. So it based on the two wavelength, the visible wavelength, and also is covered the infrared. Okay. All right. So this is a part of center frequencies, the bandwidth, okay, and also the magnetic flux, yeah, based on the UBV RI. Okay, so the important thing is you need to roughly know the center frequency. For instance, ultraviolet is about 0.35 micrometer, right? Visible is about 0.55 micrometers. So you can understand and know where is the center frequency, and at the same time what is the value of the bandwidth for each waveband. Okay, all right. So okay, I'll stop here, right? So we will continue in the next lecture, and you can ask me if you don't understand for this topic, right? So with that, thank you very much.